Okay, so welcome to the final section of the course. Now this is, this is probably my favourite part of the course really, for two reasons. Firstly, the ideas that we're going to learn today have lots and lots and lots of applications. And secondly, if you end up doing more maths next year, you'll build on a lot of this stuff. Section 5 is all about applications of integration. Well, you may think, okay, I know applications of integration. Well, probably not these ones. Probably not these ones. Today's lecture, we're going to talk about the so-called average value of a function, arc length, and if we have time, we'll talk about speed. All right, so first of all, let's motivate the topic. Why do you want to learn about arc length and average value of a function? Well, let me give you two examples. In physics and engineering, if you have a spring or a coil or something like this with a constant density, you want to calculate the total mass of that spring or coil. Basically, it's just the density times the length of the coil, right? Density times distance. So in this lecture, we'll investigate how to work out these sorts of total masses, Y's and springs. Also, the so-called average value of a function pops up in the calculation of Fourier series. So Fourier series are a little bit like series that, well, they're not quite like what you've seen. Instead of like a power series involving, x squared, x cubed, etc., these Fourier series involve cosine and sine. So if you have a function, for example, with a period, say 2 pi, I've just chosen that for convenience, the underlined series is called the function's Fourier series. If you do any second year maths, applied maths, you'll look at Fourier series. Now, here, these A0, AN and BNs, they're just coefficients that you actually can calculate via integration. Now, the constant A0 that I've boxed up is actually known. This, you can see on the right-hand side, I've basically taking the function, I'm integrating it, and I'm dividing by the length of the interval. This is known as the average value of the function over the interval minus pi to pi. Okay, so essentially average value of a function is calculated by integrating the function over an interval and dividing by the interval's length. That's all it is. Now you compare that with what you know about calculating the mean or the average of a set of numbers. What do you do with a set of numbers, right? You add them up. Let's say you have 3 numbers, you add them up and you divide by 3 to get the average. With functions, it's the same. Remember, integration is just a fancy sum. Now, the other, you might be thinking, well, what are these coefficients? Well, they're just found by integration as well. I don't want to talk about that too much, though. The point I'm trying to make is that these average value of a function that we're going to learn about will pop up. You'll see it a lot in second and possibly third year. Can I just have a show of hands? Who's actually heard of Fourier series before? I mean, independent of this course. Anyone? All right. Where have you seen them? Can you remember? Just in engineering? Yeah, okay. You'll see them a lot next year, trust me. That's all right. Okay, so the average value of a function. In general, like I said before, the average value of a function is very easy to compute. Just integrate from, A to B, whatever A and whatever B are, and divide by the length. Now, just geometrically, what does this thing represent? Well, I guess I'm going to give you a better picture in a minute, but think about this is like here we've got a function g of x, right? A function g of x. Now, essentially what we're going to do here is argue that the area under this curve is equal to the area of a certain box or a certain rectangle with a certain height. Okay, I'll come back to that in a minute. Let's actually just do a problem and find out how it's done. Okay, it seems pretty simple, and it is. It is pretty simple. All right, so here's our function, here's our interval. The average value, which I'm just going to denote by AV of f, is just given by this integral representation. All right, so here b's 2, a's negative 2. Now, although our integrand's got a radical sign, a square root sign in it, we don't have to be too fancy with substitutions. Here, can anyone suggest how we might easily evaluate this integral? Just by area, right? It's just the area of a semicircle or a semi-disc. So you don't have to get fancy here. Okay, so if you just clean this up a bit, you're going to get pi on 2. So notice that the average value of a function is a number. It's a number, it's a value. But let's actually have a look at that and see what it means in a geometric point of view, from a geometric point of view, right? Here you've got the function plotted down here as this sort of semicircular arc. You've also got, in this picture, a box or a rectangle with height equal to the average value. Okay? Now, the two shaded areas are the same. They're the same value. The area under the curve and the area inside that rectangle are the same. Okay? In other words, if I just pull this up over to the other side, on the left-hand side, I've got a box, the area for a box with height, average value of f, and width, b minus a. On the right-hand side, okay, so imagine this is up there now. On the right-hand side, I've just got the area under the curve. So basically, this setup tells you that, okay, the area under the curve can be represented by just the area of a particular box or rectangle. That's pretty much all it says. Okay, a very simple question. A more deeper result is the following, the mean value theorem for integrals. Basically, the mean value theorem says exactly what I've just told you out loud. Okay? It's got to do with areas under a curve and finding a box, the area of a box, such that the two areas are equal. So let's actually read it out and see what it says. Suppose you have a continuous function, then at some point, c in the interval, f of c equals the function, it takes on its average value. Okay, so essentially what this says is a continuous function must achieve its average value at some point. Now that's different from a list of numbers. If you have 3 numbers and work out the mean, that mean may or may not be in the list of numbers. But for continuous functions, it's different. This says that a continuous function has to achieve its mean or average value. Now, getting back to the area explanation, this, okay, think of this as representing the shaded red or pink area. This is the height, okay, so f of c is the height, and the width of the box is b minus a. So this is the area of this pink little rectangle. And we know what this area represents. It's the area under the curve. That representation that I've sort of down the bottom of the page, it says that the area, you can always find a box with a certain height such that the area under the curve and the area inside the box are the same. Now, down the bottom, I've mentioned an independent learning exercise. It's a bit vague there. Essentially, the difference between the average of, say 3 numbers and the average value of a continuous function is the function has to equal the average value, whereas the average value of a list of numbers may or may not be in that list. All right, arc length. Now here's a question just to sort of motivate our study and get us thinking about the methods we're going to use. The methods we're going to use are known as slicing methods. Now calculus basically, what is calculus? Okay. Well, a large part of it is approximating curves with straight lines. That's basically what calculus is. Okay. Using lots of little straight line segments to approximate curves and then summing them all up in a limit. That's it. That's calculus, or a big part of calculus. Here's a question for you. Suppose this is the curve y equals x squared. How would I calculate the length of that curve? How would I calculate the length of that curve? Or at least approximate the length? Any ideas? Yes. Yeah, right. Yes. Excellent thinking. Think about if I just draw these lines in here. I guess I don't need to do that. Now, if I set up a little right-angled triangle where what I'm going to do is calculate the length of the hypotenuse. Now, it's not going to be an exact match to the length of the curve, the section of the curve that I want, but it's an approximation. Okay, so if I have a triangle with sides 1 and 1, then Pythagoras tells us that the length of that hypotenuse must be root 2. So let the length of the curve be given by, I don't know, c or something. Can anyone suggest how we can get a better approximation? 2 lines, yes. 2 lines. So what I'm going to do now is, inspired by this idea, I'm going to slice up my interval into 2 parts and draw 2 right-angled triangles. Okay, I know that the pictures are a bit dodgy. So what I can do now is calculate the length of those 2 little line segments, right? And they're going to give me a slightly better approximation. So let that be, I don't know, L1 and that be L2 or something, right? So just using Pythagoras, Okay, I can work out, I need the height here, but remember it's the curve y equals x squared. So that's the length of the first one. That's the length of the second one. Now it's still going to be slightly bigger than the true value, but we're getting closer each time. So I guess the next step, instead of having two lengths to add up, let's slice it up 3 ways and have 3 lengths, and then 4 lengths, 5 lengths, etc., 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 right? If you do this enough time and take the limit, you're actually going to come up with the length of the curve. So how can calculus help here? So first let's realise that we can continue this slice and sum. So slice up the interval, form little rectangles, and just use Pythagoras. How simple is that? So what you would do here is slice up the interval, and then in the limit, add them all up, and in the limit, the width of the slices goes to 0. That's where you get your integral from in this setup. So what is it then? What is it? Here it is. This is an important formula. Suppose you have a function that has a continuous derivative. So you differentiate it, you get a continuous function. The length of the curve of the graph, y equals f of x, between a and b is just given by this integral here. So where does that come from? Well, it's basically just Pythagoras. It's Pythagoras. That's as simple as I can make it. Okay? In a similar thing, just slice up your interval and imagine this is like the kth slice or something like this. All right, so the idea is to use Pythagoras' theorem. Let's think about what this hypotenuse length is, right? By Pythagoras, this is the length of L sub k, the hypotenuse in this case. Now, what I want to do to calculate the length of the whole curve, I need to add up each of the hypotenuses, right? Hypotenuses. So let's do that, right? So add up. So let's add up the lengths. But before we do that, I'm just going to rearrange this a little bit. I'm going to divide like this. Sneaky. So what we're going to do now is add up over k, say k equals 1 to n or something like that. Can anyone suggest what the last step is? We're almost there. Any ideas? So at the moment what we've got is a sum, a finite sum, involving just the lengths of the hypotenuses. Yeah, let n go to infinity. So basically, what you're doing is the width of the cuts is going to 0. Okay, so in the limit, this will go to dy dx, this will go to dx, and the sum becomes an integral sign. By f dash of x, of course, I mean dy dx. That's how it's done. It's not difficult. You're using straight lines to approximate curves. In the limit, you actually get the length of the curve. Pythagoras. Okay. Now, will you get that in the exam? Unlikely. Unlikely. So you need to try to remember it, or I guess you could derive it if you really wanted to. Just remember Pythagoras. That's pretty much how I remember it. Well, let's see it. Let's see it at work. All right, here's a function that we're asked to find the arc length of, or the length of this curve, for x between 0 and 2. Now, anyone recognise this function? Cosh, hyperbolic cosine. So what we're interested in calculating the length of this part of the curve. Okay, so it's not difficult. Just need to calculate the derivative. Okay, so I differentiate cosh, what do I get? Sine. Now, note that the actual arc length formula involves a square root. So sometimes you've got to manage that away. Sometimes it's easy, sometimes it's not so easy. Now, can I manage this square root sign away? Yes, 1 plus cosh squared equals sine squared. Okay, so now is there a question? Oh, sorry. Oh, sorry. What am I doing? Sorry. Yep. Thank you. Sine squared. I'm getting them mixed up. Is that better? Whew. Thank you. Now, let's apply the arc length formula here. A equals 0, B equals 2. So essentially I'm just integrating cosh of x. So integrate cosh of x, I get sine. Now, if you want to write this in terms of, say, the exponential, it'll be something like this. Okay? Remember, shine 0 is just 0. That's a pretty straightforward example, right? Any questions? Now, sometimes in that particular example, it was easy to manage the square root sign away. It's not always so easy. And I'll give you some examples where it's not so easy to manage the square root sign away. Okay? Sometimes it's easy, sometimes it's not. All right, let's have a brief look at an application, getting back to the mass calculations that I talked about at the start of the lecture. Now, suppose we have a thin wire, and in particular, the wire has constant density. Now, also suppose that wire, I mean, this is a little bit sort of simplified, but imagine that the wire is lying in the xy plane and it sits along the curve or the graph of that function y equals f of x. Now, essentially, to calculate the mass for a constant density, it's just density times the arc length. So let's actually go through and calculate the total mass of this wire. So because density is constant, you can actually just pull this out and write it like this. So basically it's just density times the arc length, gives you the mass. Now next year you'll look at objects that have variable density. But here we're just keeping it simple. So what do we need? We need to calculate the derivative. So this is our f of x. Let's calculate the derivative. So let's calculate the derivative here. We're going to get something like this, which we can clean up a little bit just by cancelling off. And now let's use our formula for the total mass. Now if I square this, I'm going to get something like 8x with the square root sign. All right, so what I've got to do, I've got to integrate something with a square root sign. All right, so we don't know what the density is, so our answer is going to be in terms of the density. So we're integrating something like root 1 plus 8x. Now this is a reasonable place to be in because we can integrate that straight away. The square root sign is going to go to 3 on 2, and we just got to adjust. So if we integrate, we're going to get something like the following. So now it's just a matter of subbing in the numbers and cleaning up a bit. So if you sub in x equals 1 and x equals 0, you will, after a little bit of simplification, you'll get the following. I won't put all the details in there. Now, we're not told any units or anything like this, so at this stage it's okay to leave it, I guess, slightly open at the end with the units. Questions? I guess with a wire, you might think, how do we... I guess we're used to measuring density and mass per unit volume, right? But with a wire, it's a little bit hard to measure that. So we sort of revert back to mass per unit length. It's also like when you look at the density of, say, thin sheets or shells. Okay, you've got mass per unit area rather than mass per unit volume. Questions? All right, so it wasn't too hard to manage the square root sign away there, but they do get a little bit harder. Now, up until now, we've been using functions or curves that are of the form y equals f of x. In other words, they don't loop back on themselves. You can have curves. You can have curves that loop back on themselves, right? So this curve here, let's say it's a, I don't know, it's a wire or a part of a spring or something like this. It loops back on itself, so it's not a function. You can describe these kinds of curves, though, with so-called parametric equations. Now, what happens there is you have some sort of variable t that's known as a parameter. And each of your coordinates, I guess your x and your y, they each have a function that sort of describes what they do, basically. Now, can we look at arc length for these kinds of more general curves? And the answer is yes. And it's just a slice and sum technique. Now, the following formula can be used when you have a so-called parametric curve or parametric description of a curve. So we've still got an integral involving a square root, but instead of having f prime, or I guess dy dx all squared, we've got the derivatives with respect to t in here. So f prime of t means df dt. G prime of t means dg dt. So where does that come from? Well, basically all you do is you go in here, right, and you divide everything by delta t sub k, right? Put those into the squares and pull one out, and in the sum up, and in the limit, so essentially what you do is you sort of have that, okay? And then if you sum up it in the limit, look what happens. That goes to that, that goes to that, that goes to that, right? You sum up, and the summation goes to the integral sign. Anyway, I'm not going to derive that for you, but let's actually look at a real simple example. Suppose you have the following parametric equations. So here's a real simple example of a parametric setup for a particular curve. Anybody know what the curve is? It's a circle, right? It's a circle with radius 1. And the parameter t parameter t is just the angle to the positive OX axis, and the circle's drawn out in an anti-clockwise direction. So as a simple example, so as t sort of goes from 0 to 2 pi, you sort of go in an anti-clockwise direction. So as a simple example, let's actually go through and apply the arc length formula to calculate the circumference of the circle. Now we know what it is, of course, but let's actually just verify that it works, and let's just keep it simple. So now, if we square these and add them up and take the square root, what are we going to get? 1, right. Using cos squared plus sine squared equals 1. So the circumference so it's just 2 pi, right? That's real simple, real simple. You'll look at much more complicated parametric forms next year or at some point. Let's get on to something slightly more practical. Pendulum clock. Now, back in the day, building accurate clocks were important, right? What's up, guys? Is everything all right?
Yeah, no.
Yeah, you cool? You all right, man? Yeah, all right. Back in the day, building accurate clocks were really important to, for navigation purposes and just to keep correct time, right? A lot of scientists and engineers and inventors tried to build an accurate pendulum clock. Now, the biggest mistake that was made was trying to get the bob, which you can do, it just swings from side to side, to swing in the arc of a circle. Now, the problem with that is that the further you start the bob away, the longer it takes to sort of, its swing depends on how far you sort of let it go. Now, Huygens came up with the following. He said, okay, let's not get a circular arc here. Let's slightly modify that. So that the cycloid arc is not a circle, it's like it, but it has the beautiful phenomena that no matter where you let the bob go from, say here and let it go, or up here and let it go, it takes the same time to complete a swing. That's a bit counterintuitive. I don't know, most people don't believe that when they hear that the first time. Okay? So think about this, if you want to keep it simple, think about this curve as like the side of a hill. If I have someone who starts here and runs and say, bicycles down the hill, and someone who starts here and they fall under gravity, they will both get to the bottom at the same time, irrespective of where they start. Anyone heard of that principle before? Yeah, it's a bit strange, but it works, okay? So what Huygens did was, imagine this is a thin piece of wire. He put these guards in, so what would happen is when the bob swings, it would sort of get caught up and move away from the sort of circular motion. Now the curve like I said before, is known as a cycloid. So for the clock, you just have the cycloid sort of, round the other side of the axis. You can form a cycloid by imagining you've got some sort of circle and you just roll the circle along the axis and you've got a point on the edge of the circle. So here's a parametric representation of a cycloid. Here's the general one. Here A equals 2. You're asked to calculate the length of one arch of the cycloid. So can I have a show of hands? Who's heard of a cycloid before? Anyone? Yes, where have you heard of it? Say again? Excellent. Where have you heard of it? Okay, yep. From an engineering and design point of view, cycloids are really important because they can be used to form arches in fancy buildings. Anyone been to London here? Anyone? All right, St. Paul's Cathedral. Okay, if you go into St. Paul's Cathedral, you'll see arches everywhere. Now, the guy who designed St. Paul's Cathedral, Sir Christopher Wren, he actually was the first person to solve this problem, and he thought he'd celebrate by putting some of the results in his architecture. He's just showing off. So this is a pretty famous problem. So let's actually see if we can answer this question. Now, this is a hard question. I'll show you exactly why it's hard in a minute. It's managing away the square root sign in the integration. So this is our little f of t. This is our little g of t. Let's calculate the derivatives and see what... All right, so if I differentiate, I'll get something like that, if I'm not mistaken. Differentiate over here, I'll get something like minus 2 better. Okay, so let's look at the squares of these and add them together. See if we can simplify somehow. So it looks okay at the moment. So I guess I can do this. All right, so if we square, I get something like this. Now, when I expand the first bracket, I can use cos squared plus sine squared equals 1. And so I'm going to simplify down to the following. I'm going to simplify as much as possible. So I haven't put all the steps in here, but it's just a matter of simple algebra. All right, now, the problem is, how am I going to integrate square root of 1 minus cos t? Everything's been okay up until now. So let's write down our arc length. So it's the integral of this with respect to t. Uh-oh. How do you integrate square root of 1 minus cos t? Yes. Even simpler than that. Yes. Oh. Yes. Oh, yes. Okay. I think that's what you were saying as well, right? I misunderstood what you said. Yes. We can use a double angle formula, okay, in the following way. It's not like a double angle formula. I think it's like that's what you meant when you were saying half angle formula, right? Was it? Yes. Okay. Just say yes. Yes. Good. All right. So the following can be used repeatedly in these kinds of questions? Oh, you over there. Now, how does that help us? Well, we've turned 1 minus cos t into the square of something. So we can eliminate the square root sign in the integral. That's the important step here. That's the important step. So let's put that in. So I'm going to pull out all the constants, replace that with sine dt. I don't need to worry about absolute values because the interval's okay for that. So all I need to do now is integrate sine of t on 2. Now, if you plug this in, you'll get 16. Yes? What's that? No, because the root 2 comes from here, right? And then that hooks up with this root 2, so you get 4. Yep. Now, think about it. 16, it's kind of a nice round number. Is there some sort of general method? Well, there is. I'll let you to think about that if you want to. But yeah, according to my knowledge, Sir Christopher Wren, the great designer, architect of London after the massive fire in 1666, I think, used cycloids in designing things like St. Paul's Cathedral. It's pretty amazing stuff. Questions for that one? This is the best. This is awesome. Knowing this, it's almost impossible to do that question without introducing this squared term. Speed is another application of arc length. Now, this isn't in your notes. When I reviewed this again, I just added a couple of sentences to give it a sort of more thorough treatment. You don't need to copy this down, but it will sort of help with the understanding in the following context. So suppose we've got a particle moving in the plane along some sort of curve. So we're in the plane, in the xy plane, we've got some sort of curve, say, and we're moving, say, in this direction, along that curve. Now, at any point on that curve, we can associate a position vector. So this sort of parameterizing function here is actually, say you're there, some sort of position vector to the origin. So as t changes, your vector r will move along and trace out that curve with its little pointy arrow head. Now, you may have seen this before, you may not have. If you have this kind of parameterization, this kind of setup, you can calculate the velocity of this particle moving in two-dimensional space. So you just basically look at the derivatives with respect to time. Now, the speed of the particle is just the magnitude of the velocity. So if this is the velocity vector, by these two sort of parallel lines, vertical parallel lines, I mean the magnitude of the vector or the norm of the vector. Okay? So that's how we define speed, the speed of a particle. So how does this actually relate back to arc length? How does this relate back to arc length? Well, so don't worry about this too much. This is not bad though. But does anybody know what does geometrically does this v vector represent? Huh? Well, it's just a tangent. So if you had a tangent sort of vector, all right, to the curve in the direction that you're going. Anyway, don't worry too much about this. What we're interested in is relating this back to arc length. Now, if you calculate So say you're moving along your curve C. You want to calculate the distance that you've travelled, right? So how can we do that? Well, let's say we want to measure the distance that we've travelled between a point, say t0, say t equals 0 or something, and another point, the arbitrary point t. All you have to do is calculate the arc length. But instead of integrating from, say, A to B, you're integrating from some initial time, t0, to some arbitrary time t. Okay, so that's where that d of t comes from. Now we know that the speed of a particle is just the rate of change of distance with respect to time. So if I have some sort of function for distance, then I can just differentiate it, right? Now in your notes, I think I've got S's instead of big D's or something, but anyway, it doesn't really matter. And the proof that, as we looked at it yesterday, was just to basically apply the fundamental theorem of calculus to this starred expression. Okay, so we know that basically we're differentiating an integral, so you just remove this and plug in t for u down here. But let's actually look at a problem where we can use these ideas. Let's do a problem. So by FTC, I mean the fundamental theorem of calculus. All right, so something that you might get in end session. So the next example is a good example. So we've got a curve described by this parameterization here. This the curve's sort of parameterized this way. The time t is in minutes, and the distance is in meters. First of all, determine the speed of the particle at the instant time t equals 1 at 1 minute. And secondly, determine the distance travelled after 4 minutes. So let's do part A. So guys, I can hear you down here. Be quiet. Okay? So let's just differentiate and apply our speed expression. So x prime is just going to be 2. Y prime is going to be something like this. So all we have to do is square them, add them together, and look at the square root. So let's just square and add and take the square root. So we're going to get something like this. So that's like the speed at any instant, any time. What we're really interested in is the speed at a particular point in time at t equals 1 minute. So just sub in t equals 1. That's better. Woo. Thank you. Who said that, by the way? Thank you, both. Now, distance travelled after 4 minutes. Okay, so all we want to do is integrate this from 0 to 4, right? So now remember, a lot of these problems involve managing away the square root somehow, but it's not too bad with this because we've got a linear part in here, so it's not too bad. So if I integrate now, the power's got to go to 3 on 2, and then I just need to adjust by some sort of, toing and froing with the factors. What's that? Yeah. Well, where's my working out? I haven't done anything, right? So you should be able to do it by inspection. I mean, basically, you know that it's going to look something like this, and then you just got to multiply by an appropriate constant. I mean, that's how I do it anyway. So just sub in now, t equals 4 and t equals 0. We're going to get something like this. And if you clean that up, you should have something like this. So that'll be in meters. So assuming you can do your basic calculations, these problems aren't that hard, okay? They aren't that hard. They're pretty easy marks, really. They're pretty easy marks. Now, will you get the formula for speed in your exam? Unlikely.